Okay, so we'll talk about the equivalency between the PDA and CFL, context free language. So we'll see if a language is generated by a context free grammar, then we call that language is a context free language. We'll see that this is they are equivalent, like given a context free grammar, given a context free language, we can generate a that means they will that will be generated by a context free language, a context free grammar, and then we can construct a corresponding PDA which will accept the same language. Acceptance may be in either by acceptance by stack, empty stack, we will see by empty stack, but both are equivalent. If it is empty stack, then we know how to convert that to the acceptance by the final state. So, so let us talk about this a context free language. Context free language CFL. So, given a sigma, which is the input alphabet or terminal, sometimes we say this is a terminals in the sense of context free grammar. So, what is a context free language? It is a string of terminals or string of alphabets, input alphabets, such that we have a grammar G, which is V T P S. This is a context free grammar. Such that it will generate the language L. Okay. So, what is L of G? L of G is nothing but we start with set of all string of terminals, all string of terminals such that we start from S and we should able to the derivation we should able to reach to W. This is called our the grammar generated by this context free this grammar generated by this CFG. Okay. And if given a grammar, if we have such a given a language, if we have such a grammar, then that language is called context free language. So, now we will come to know the equivalency between the context free language and the PDA. Given a context free language, we can construct a PDA which will accept the same grammar. So, that we will see, and for that we need to take this grammar in a particular form, which is Gabec normal form GNF. Even if it is not in GNF, we can construct that also we will see, but first let us take this grammar in GNF and then we will try to construct a corresponding PDA which will accept the same language. So, let us take a grammar G, which is basically V T P S. This is a let G be a context free grammar in GNF in Gabec normal form. So, Gabec normal form means all the products, we know the two normal form, right? One is CNF, another one is GNF. Okay. So, what is GNF? GNF is nothing but all the these productions are of this form. A is going to A alpha, where A is a terminal and alpha is a string of variable, then since it is star, so that means alpha could be epsilon also. Okay. Then if all the productions of this form, then we call this grammar is in GNF, Gabec normal form. So, for example, we have seen some example of a Gabec normal form, like if we S is going to say 0 BB and B is going to 0 S 1 S or 0. So, if you see here V is nothing but we have two variables and terminals are 0 and 1 and the productions are of this form. There are so all the production, like if S is this production, if we take, so this is of this form that some symbol is going, some variable is going to alpha, this is alpha, some terminal alpha. This all this like this, even B is going to 0, this also, because this alpha could be epsilon, because this is the coming from V star. So, string, this string could be null string also, okay. String of length 0, null string. Okay. So, we have given this, and all these are of the form in the Gibbon normal form. Now, from here, so how to suppose it is generating the, suppose there is a L CFL L for which we have this, that means L is equal to L of G. L of G is nothing but set of all string such that S is derived derivation tree, if you recall, leftmost derivation, rightmost derivation. So, here we will use the leftmost derivation to prove it. So, anyway, let us see that. So, this is going to this. Okay. Now, we want to generate a grammar, a PDF, a PDA, post down automata, which will accept the same L. So, from this we want to generate a PDA which is Q sigma. So, sigma will be T here. Okay. So, Q is, we are only take the only one single state. So, this will be Q only one state, this is one state PDF, and sigma is this, and V, if you recall, the PDF is of this form Q sigma, then this is the symbol stack symbol. So, stack symbol we are going to use the variables as a stack symbol. So, we will put the variable into the stack, okay. And then we have a delta we have to define, so that it should accept the same language. We have only one variables, only one state. So, Q is the starting state as well, and if you recall, this is delta, Q0 was there, Z0 is the starting symbol of the stack. Now, here S is a special symbol, S will be using the for the starting symbol of the stack, and then we have a set of final state, but here we are going to show this acceptance in terms of the empty stack. So, that is why we do not care about the final state. So, we will put this part to be empty. We do not have any final state, because we are going to show that this language of this in the with respect to the empty stack is same as L. Okay. So, what we are going to show, we have to define this delta. We have to define this delta such that the language accepted by the empty stack is same as L, which is L of G. This we are going to show. Now, let us define delta. So, delta, what is the input of delta? So, delta will take some state Q, there is only one state Q, and it will read a input symbol, say A, okay, and it will read a stack symbol on the top of the top of the stacks. This is some Z, this is a variable. So, this will be some A. Okay. So, delta is of this form Q A is same as T, which is sigma basically, and we have A. And this will replace to what? So, this is a non-deterministic move. So, this will be going to so this will be going to some this will contain this q, and this A will move to gamma, where we have a rule like this, A is going to A gamma. Okay, where A is going to A gamma. So, this is the way we define this. If A is going to A gamma is in this is in the P, then we have a this delta corresponding to that. Okay. So, now with this construction we can show that they will accept the same language. So, with this construction we can show they will accept the same language. That means, whenever we have a rule like this, A is going to A gamma, then we will have a, then we will say q comma this, then we say that delta of q A contains q comma gamma. Okay. Q is the only one state, so it will hop in that state, but only thing it should do some changes in the stack, and slowly we have to empty the stack. So, this is the way. Now, it can be shown that if we do like this, it can be shown that our claim is, it can be shown that S for the gamma, if S is going to x alpha in the by the leftmost derivation, if and only if, means this is if this is happening, then this will happen. If and only if we start with q with the input x, and with the start symbol in the stack S, this will reach to q. We do not care about the state alpha. Okay. This is true for all x, and all alpha belongs to V star. Now, if alpha is empty, then this is the string of language generated by this grammar, and also this is accepting by this q epsilon alpha. So, this proof is not I mean we can easily verify this proof. Okay. So, now we will take our example to construct such a PDA. So, let us take a grammar which is in GNF. So, suppose we take a grammar, the one we have, and B is going to 0s, 1s, and also 0. Okay. And what are the variables we are using? So, this is a grammar V t and P s. V is s comma b, and t we have 0 1, and we have this s. S is the starting symbol, and these are the rules. So, this is in GNF. Okay. Now, we can see that this is a string 0 1, then 4 zeros. This is a string accepted by this, generated by this. How we can generate this string? We can start with S, then we can use this rule 0s, then we can use the leftmost derivation, because The way we are constructing is by using the leftmost derivation. Then this s again we can there, since there is a 1. So, we can again replace this by this rule. So, 0 1 s again, then this s again it is sorry, this no, not s, this is b, sorry, made a mistake. So, s is going to, so this is not s. So, s is going to 0 b b. Okay. Now, since this is a leftmost derivation we want to do, so this b we can replace by either one of this, but we have to have this 1. So, we will take b is going to 0 s, this move. So, 0 sorry 1 s, 1 s b. Now, again this s we can go to, we have only one option 0 1 0 b b. Okay. So, 0 1 0 b b. So, now we can have so now after this we can have this 0 1 0 b b, and we have a b over here, sorry. So, now we can take all the b's to be zeros. So, we can take first this be 0. So, 0 1 0 0 b b, then we can take this b to be 0, then 0 1 0 0 0 b. So, this is the leftmost derivation, then 0 1 0 0 0 0. So, this is a string in the language generated by this. So, this in short we can say 0 1 0 to the power 4. Okay. Now, we will construct the corresponding PDA, which will accept the same language. So, how to do that? So, we will just take m q 0 1 phi. Okay. In the way we constructed, that is the only one state we have, and this is the terminals, because terminals are just the input alphabet 0 1, and then we have this stack symbol S B, which are basically the V delta like this. So, now let us define the rules. So, rules will be coming from the this. So, now S is going to 0 B, this will give us the rule like this. So, we are state is same, we have only one state. Now, if we see a 0 and if the stack symbol is S, so this will be containing q b b. This is q b b. Okay. And we have from this we can say with the state is always same, b is going to 0 s. So, that means, if we see a b over here, this will contain there are yeah. So, with 0 we have this and this. So, here nothing means it is epsilon. So, it is q s for coming from this rule by this production, and we have b is going to 0, from here we have q epsilon. These two rules we have. Okay. And now, we have a b is going to 1 s, from there we can say that delta of q comma 1 comma b, this is going to 1 s. So, that means q comma s. So, these are the rules. So, with this rule we will try to accept this this string 0 1 0 to the power 4. We will try that with this transition rules we can accept this. So, For that we start with Q, we put this into the tape and then our starting symbol is S. Okay. So, this will go to where? This will go to, so 0. So, we first read a 0 Q 0 S. So, Q 0 S, Q 0 is will go to this. So, that means this S will replace by B B. So, Q will be remain. So, 1 0 to the power 4, S will be replaced by B B. Now, we have a 0 here, B here. So, that means delta of Q 1 B. So, Q 1 B we have a only one option. So, Q S. So, this B will replace by S. So, this will go to Q 0 to the power 4 and this B will be S B. Okay. Now, again this will go like this. We have a 0 over here. So, Q 0 S. So, Q 0 is again it will go to Q 0 to the power 3 now, S is going to replace by B B. So, 3 B's B B B. Okay. So, now again this 0 B. So, 0 B, yeah, now 0 B we have few options. We can we have two options over here, 0 B, Q 0 B, we have two options. So, we can take S or we can erase that B. So, we will do that. So, Q 0 square B B, and another way is Q 0 square S B B, two path is coming. Okay. Now, let us follow this path. We need to converge in at least one path, then that will work. So, this will be like this. So, this is again Q 0 B, we can take this rule. So, this will be Q 0 1 B will be this erase, then again we can take this rule Q 0 B. So, it will be Q epsilon epsilon. That means, this is accepted 0 1 0 to the power 4 belongs to enough m. Okay. So, this is the construction for this. So, we can have another construction corresponding to this, but not in general, I mean which may not be in the GNF. So, that is we are calling the alternative construction. So, this any string which are accepted by that grammar can be accepted by this automata. Okay. So, alternative J construction. Alternative construction. So, suppose G is not in GNF, or even if it is in GNF, we will not consider that. G is not in GNF. That means, we have a given a G. So, this is T. Now, we construct a grammar a PDF like this. So, we will take a same, but only thing here the stack symbol we are going to put as V union T. Delta we are going to define, Q is the only state, S is the starting stack symbol like this. And here we are going to define delta as like delta of Q comma epsilon comma A is containing Q comma alpha if we have a rule A is going to alpha in P. Okay. So, here it is okay, because our stack symbol is containing V as well as T. So, it is coming from V star, I mean V union T star. And the second rule is delta of Q A A this is nothing but q comma epsilon if this for every a in T, for all a in T. So, if you have a terminals, then it will be q comma epsilon. Okay. So, with that we can have a construction like this. The same example we can take, but using this alternating construction. So, S is going to 0 B B and B is going to 0 S or 1 S or 0. Here we do not care about whether they are in GNF or not, although they are in GNF, but we will have this construction, this alternating construction. So, we have a Q over here and this is the 0 1 terminal strings, and here the symbols are V union T. So, V union T is this and T is 0 1, that is the difference, delta is phi. Now, how we define delta? So, delta of q epsilon s, it is nothing but q comma 0 B B. Now, we are allowed to use the string of terminals and the variables, and delta of q epsilon b, which is same as q 0 s q, just the rules, just the production will give us this q comma 0. Okay. And for the terminals, this is 1, and for the terminals what we say, delta of q 0 0 is nothing but q comma epsilon, and delta of q 1 1 is nothing but again q comma epsilon. And we can easily check that this is accepting this string 0 to 4, that we can easily verify. Okay. So, this will be given in the lecture note. Thank you.